Hi, welcome everybody to a new video, and this is a new series that I decided to do. It's called CST Tutorials. It will be a new playlist in my channel. And what I want to do here in this tutorials is to show you modeling of different structures in CST Studio. I will start with the differential pair today, and I think the key, or what's the difference actually to other tutorials which you will find on YouTube, is my speed. Because I think I'm pretty fast using CST Studio, and I will try to teach you a few of keyboard shortcuts to make you more efficient in modeling and working with CST Studio. So let's start right away. As always, this is CST Studio. Select a new template. And for today, I will go for this EMC template. Of course, you could do also the EDA templates, but EMC templates are actually written by me, and I like them very much. So we go to EMC, EMI components, and our generic PCB templates. That will be fine for us. We use 3D simulation. We will be in the low gigahertz range, so frequency domain solver will be our choice. Units, millimeters, gigahertz, nanometers. And we go from 0 to, let's say, 3 gigahertz. Let's add a few monitors just to make stuff visible, and that's it. That's the template we would like to use, and the template does a lot of settings in the background. And now the 3D view is opened. And first of all, when I work with CST Studio, I keep always here the zoom mode, so my mouse drag is zooming in and out. If you had space, you always zoom out to the structure, and then I use Control for rotation and Shift for the rotation in plane. So they are two different modes of rotation, and with these keyboard shortcuts you will be much faster. And if you hold Shift and Control at the same time, you can pan. For zooming, of course, I will use a lot of mouse wheel forwards and backwards. So let's save the model before starting. It's always a good idea. Call it diff pair. Okay, here we go. And I start the modeling. So first I draw the ground plane, just a simple rectangle in the plane. Start here. Let's make it maybe something like 60 centimeters, minus 30, 30, 0, and the thickness 0.035. Let's call it thick metal. So I parameterize. I can parameterize in every menu here. I don't need to define the parameters up front. I can define in the box. We load the copper material from the library. That's fine. GMD1 thickness metal. And now it's asking me, of course, what's the thickness of the metal, because I have parameterized and the parameter was not present. So 0.035. Pretty straightforward. And now I build a stack up, and I built the stack up by using extrude functionality. There are different ways, of course. You can import ports, but that's we doing modeling today. So I pick the face, which is shortcut F, extrude with let's call it thick substrate sub. And we load some FF4 material from the library. Okay, preview. Thickness substrate will be 0.2. Okay, here we go. I don't like the color of our FR4 in the library. So let's go to the materials and make it green. As every good FR4 material should be green. All right, now we build a stack up. So I take this one. So I want to move the whole stack up. So I pick points, that's P. And if I pick the points and then do a transformation, which is Control T, it's moving. The vector will be the points I have picked. And copy. We got already this one. And let's define another metal layer. So doing the same way, I again pick. It's a very interactive way of working. It's maybe not the cleanest, but a very interactive. Or you can do a right click and transform instead of hitting Control T and copy it again. So we got 3 lines, and what's missing is the substrate at the bottom. So let's move the substrate. I want to have, of course, towards this point should be this point of the substrate. Again, transform, invert direction because I picked the one first, and copy. Okay, this gives us our stack up at which we like to work. And now I want to define the trace as the differential trace. There are different ways, and I will do it differently. But first, we want to work on the top of the substrate. So I double click the substrate and I pick the face and then align the working coordinate system. And now it puts my plane on top of this one. And I want to be in the center, so I push M for the middle point of the edge and move my coordinate system here. That's just for convenience. And now I can draw a line. So I go into modeling and I say I draw a line. And you can, while you're in a definition of a shape or the definition of a line, you can still use picks. So I pick the middle point again. And if I hold shift, it gives me a straight line. And we go up to the center of the substrate with a 30 millimeters. That's it. And now I define a trace out of it. So select the curve. All right. The thickness, which is actually the height. So let's call it trace thickness and the trace width. And it should be copper, of course. So trace thickness will be the same as before. Trace width 0.4. Nice signal trace. And I want to make it differential. So I take this one and I transform it again. So you have this nice handles, but I parameterize it, call it separation. All right, will be 0.8. Okay, we got the one line down there, and we do the same thing, transform, move it via separation times 2, copy the shape. Okay, maybe that's a lot of separation, so let's reduce this. So I changed the parameter, I have to update the structure. Yeah, now it's better. So we got a differential trace pair we want to have, and now first of all we calculate the impedances, and we use a so-called waveguide port for this. So let me hide the local coordinate system, and now again I use picking for the waveguide port. So I pick the face with F, and I pick the middle point here again with M. This gives me a well-defined plane. Oops, not a discrete port, we want to have a waveguide port. You see, now it's defined the plane. Of course we have to make the port bigger. It has to capture the whole mode pattern. It's too small right now, so I add some distance down here, down here, down here. That's the wrong direction. So up here. Now I got the right plane. Now this mode will capture, this port will capture the complete mode, and we will define so-called multi-pin ports. So we want to define different mode patterns. Of course, differential mode. So I said my set 1, the differential mode is positive on this one, and it's negative on this one. And the second, the common mode, is positive on this one, and of course positive on the other one. That's the common mode. Okay, now I've defined the both modes on the waveguide port, and we can calculate the port mode. So I go to the frequency domain solver, I disable this setting for low frequency simulations we don't require, and I set calculate port modes only. Now it's calculating port modes. It's calculating the mode pattern in this this plane, in this red plane. So it's a 2D field solver, which now calculating the mode distribution, and we can see them once it's finished. That's it. You can see the port mode here. Don't bother about port mode base. Port 1, 87 ohm, higher, tightly coupled. It's still a differential mode. You can see the electric field pointing from here to here, but of course tightly coupled to the ground plane. So 87 and 25 ohm. Very nice. That's what we want to have. And now we add a via transition. So I again use my working coordinate system. We want to place a via, so I'll pick this middle point here with M again, move my working coordinate system to there, and draw the via. I draw it by a simple cylinder. So again, during picking, I'll pick middle point, have the via here. Now I need the end of the via, so I go to the other side and I want to align it with the end of the substrate. So I hit A for picking the center point of the substrate, and it gives me exactly the right length. I don't want to do a hole in the via, but I want to have the via radius parameterized. Via red. Okay, it should be copper. 0.2. It's a little bit small. I have to delete the results because I'm changing the shape. Okay, why not? It's the same thickness as the trace, and of course I need the via on the other side. So I use the same way I was working before. I pick the middle point here, I pick the middle point here, I click the via and I transform it, copy it, and I got the via on the other side. And of course we now need to define anti-vias, right? We need to put holes into the metal layers that are here. So if you are like this, if you hit 1, it will align your view to the axis, to the closest axis that you have selected in the view. So of course we need to put holes into these 3 layers there. So let's do it. It's very simple. What I do is I pick the face height, the substrate, it's in my way. Control H hides the selected shape. Now I have a nice view on the via. I pick this ones and I choose extrude. Of course you can define it in a different way, but as you wish. I do it this way. We place vacuum here, anti-via thickness, let's say 0.2. Okay. Let's make we don't care about this. This is just the intersection. Let's make it a little bit thicker. So we create a nice hole. F7 for updating. Wow, that's big. Actually, I wanted 0.3, not 0.8. Here we go. And now we have to cut them out, right? So I select, double click the plane. Okay, double click the plane and hit the divide button, which is an insert command. This one and this one should be inserted into the shape, exactly. Control H, height, there's the next layer, divide, select, hit enter, we got our hole, Control H. In the substrate we don't need to do this cutout. In the metal again, divide, select, and hit enter. Now I got my holes. I don't need to care about this inner because it's overlapping with the via. So I got my holes, I got my anti-vias, I got the input here. We don't care too much about this vacuum blocks that I used to cut out, but we want to now draw the other end, right? So I again align my coordinate system down here to make it work. And now I want to start at the center and I want to do something more fancy. So I don't want to have the straight lines how I constructed it before. I will construct it now in a different way by using a so-called sweep. So first I want to align my path, my sweep path to the center between 2 vias. So I pick this point, I pick this point P for picking, and there is a nice option in the pick points which says mean last 2 points. So now I'm in the center. And that's what I want to draw. So I draw a polygon, something more fancy, to get some length mismatch, okay? You will see how that works. So that's the polygon. We start at 0, 0. Now I draw a little bit of freestyle. But I want to add perpendicular and the line perpendicular to being able to define also a nice waveguide port. We have to correct it a little bit. We'll start at 0 because 0 is the center where I have picked, and we would like to end at 30 because that's the end of the substrate. Okay, that's my polygon. And now I will draw the 2 lines. I will sweep them, but for this I need to draw the profile of the lines. So I take my working coordinate system. 0 is wrong. I had to start here. So what I forgot is I wanted to align because I wanted to start here. But don't worry, we go to the history list. And before, so pick mean point was here. So I run my model down here, you can see. So the structure is always constructed by a history list. All the command I'm putting in there are in the history list. I picked the mean point, and actually I wanted to have my working coordinate system align with the mean point. So I can do it. I run the history list before the curve definition, and now align it here and update the whole thing. And my curve polygon will start at the right position now, as I wanted it before. Maybe what I don't like is that the first section is at a corner, so no problem. Go back to the line, double click the polygon, you go back to the definition of the polygon. And instead of having this slight angle, I go to 0 here. Here we go, now it's straight. Then it does this kind of meander and it's straight again. Okay, so we have corrected the line. You can see you can always go back into the definitions you have done just by simply double clicking the tree. Now I need to define a path. I need to define the two rectangle tracers which will be swept, and for this I have to rotate my working coordinate system, because right now I'm working in the plane. I have to work in a plane perpendicular to it. So you can of course do transform and rotate it, but you can also use your keyboard shortcuts. So Shift U, Shift V, Shift W rotates by 90 degrees around the given axis. So all I need to do is Shift V, and now I have rotated my coordinate, my working plane. It's now perpendicular, and now I draw these rectangles. Okay. So I draw the first rectangle over here. And of course, we want to start at 0 and have the trace thickness, and start at, we're going in the W direction, so W min is the separation divided by 2, and this is the separation divided by 2 plus the trace width. You see it's doing autocomplete. I don't need to type everything, but now it's pointing downwards. Yeah, because U points downwards, so I need to do minus trace thickness and 0 because it's pointing this way. That's exactly what I need. I have my first rectangle, and now I'll take the second rectangle, just transform it, copy, and go minus separation, probably separation times 2. Exactly. That's what we want to have. And now I have my two curves, the two rectangles, which will give the profile, and a path, which is the polygon, but I need to separate them. So I need to define a new curve. Just drag and drop the polygon down here. So in the tree, you can drag and drop. And now I define a so-called sweep curve. So double click the profiles. You can also choose the tree. So that's our profiles. And what is the path curve? This is the polygon. Here we go. Now I have these traces, and now also the different lengths, right? They're going inside on the outside, and that differs the lengths. Just name it differential meander. It should be copper. All right. Now I have a more fancy trace on the other side. Control U does show all the shapes, because I have hidden the shapes in between. So we are back here, and I have to define another waveguide port. So F and F for picking the face, M for picking the center. Similar, basically the same thing we did on the other side. Now define the waveguide port here. So distances 5, 5, and 5 to here. Multi-pin port with positive. I don't care about the face right now, so I'm not checking which side was positive and which side was negative on the other port. And then the common mode over here, and the second common mode for port 2 down here, positive positive for the common, positive negative for the differential mode. Okay, now we are set up to go. I get rid of the local coordinate system. Alt W lets you hide the working plane just to make you look more fancy. So looking all good. We have the anti-vias, we have the vias, we have a nice differential trace on the other side. So we should be ready to start the solver. We would like to have all the modes, and not only pod modes, but really everything. Adaptive mesh refinement. We limit the adaptive mesh refinement. I don't want the simulation. I want the simulation to be very fast. It does not need to be accurate because it's only about showing you the modeling and the workflows that I'm doing. So now the differential pair is solved. So again, it's starting with a port calculation. As you can see, port mesh refinement. So in the 2D plane here, first the modes are calculated. We have seen the modes already previously. Once it's finished, we could go here. It's not yet finished, so it's the port mesh refinement. Should be done in a second. And we can check, for example, if the modes are the same on the two ports. Obviously they should be, because it's the ports has been defined in an equivalent way. So now we can go here. So port 1, differential mode. $87 ohm. Port 2, no, that's still port 1, common mode, 25. You can also see these values, of course, in the port information here in the line impedance. So I'm doing everything while the simulation is running. You can see here 87 and 25 at 3 gigahertz, but of course at other frequencies, due to the dispersive properties of the material, the mode will be slightly different. Okay, so that's why you see that this mode here, I mean, this is also very low frequency, while over the, let's say, signal frequencies, it's almost constant. Just at this very low frequency where it was calculated something, I think one megahertz, that was a different value. And for the adaptive meshing, we can check. I have limited the adaptive meshing. You can see, like, okay, in the beginning with the initial mesh, that was far too coarse, and after some adaptation we get something like 15% in the S parameters. It's still not highly accurate, but it should do it for today. So you can check this in the tree under adaptive meshing, and now the solver runs. Now it's calculating the S parameters. So you have this axis marker. You can move around to read the values, the actual values. I hide it now. The good thing is, I mean, the solver is still running. You see in the background here in the message window, it's running, but I can already check my results. We are at sample 16. It should be finished soon. So you can see this is the differential mode transmission. So we go from S1, port 1, and in the brackets you see the mode, which mode 1 was the differential mode. So the transmission from port 1 to port 2 differential mode obviously shouldn't be that bad, even if the channel is not well designed. Of course, it's not well designed. And the common mode transmission S1, 2 for the common mode. Obviously at DC there is no common mode transmission. It goes down here. So that's fine, because our planes, they are not connected to each other. There is no stitching via around it. So that's why you don't have a common mode transmission. But that's it. So the S parameters are calculated, and of course we don't want to stop at the S parameters. So we switch from the 3D view to the schematic. And now you see on the schematic I have a block. Basically in this block there are all our S parameters, and I have the ports. So port 1, mode 1, port 1, mode 2, and the same on the other side. And we would like to see some signals, right? So I hit P for a port. It gives me here, and I terminate the others. Shift R gives me a resistor. So terminate the common mode impedance with 25 ohm. G gives me a ground for the termination. Same thing, Shift R, G and G. Let me build this structure. We terminate with 100 ohm for the differential mode and 25 ohm for the common mode. That's it. And let's now define a transient task. So we want to add some switches. We will drive the differential mode at port 1. with a, let's take a PRBS signal. So 1 volt, that's fine. Rise time maybe 0.2. So I have to be careful, of course. I calculated up to 3 gigahertz, so I cannot use, I mean, the rise time of 0.1 is already, if you look at the frequency content, so 0.1 is 10 gigahertz divided by 3, so something like 3 gigahertz. We are close to the limit of the simulation. That's why I will use 0.2 for T rise and T4. Let's set the T pulse to 2, something like that. And the transient simulation should run for 20 nanoseconds, and I will use my EDEM vector fitting. So you have to do vector fitting. You have to take the S parameters and convert them to a SPICE model, and EDEM is, I think, the best tool around on the market. So I switched to this, to EDEM. Now it's doing this. You can see down there, it's saying vector fitting. I forgot to place probes. So the problem is we just see the voltage at port 1 and that's it. Oh, it's 14. Wait a second. Sorry, my signal definition doesn't seem to be what I want to have. T pulse is 2. Okay, no, that's fine. First of all, we place probes. So I click on the line and O gives me a probe. And okay, this is the diff transmission. This is the COM transmission. And this is the COM reflection. My PRBS didn't look that well. Let's run it one more time. Yeah, that's what I was looking for. Now we have the really longer signal, and we see, of course, not the nicest signal, a lot of overshoots, but that will do it. So port 1, this is how we're driving with the rectangular signal and the differential transmission, and we can also see the common mode, right? The reflected common mode and the transmitted common mode. Okay, there is, of course, some common mode due to the setup. I thought there was a warning. You can see dispersive block is calculated up to 3 gigahertz, but it used to 5 gigahertz, and that's my problem. My signal was a little bit too fast that I have used here because my 3D simulation didn't do broadband enough. So let's make it a little bit. Let's make the rise time a little bit less. We should get no warnings now, exactly. And probably also our signals should look a little bit better, not that much. So okay, we got this. We see the transmission, we have some PRBS, but we also would like to see, of course, an eye diagram. So what I do for the eye diagram is I need to first calculate the step response for a statistical eye diagram. So I do the same way as before. I define a step excitation. So here 0 T delay, T rise was 0.4, 0.4, T hold 20, T total 25, and then we run for 20 nanoseconds. So the step response will be used by the eye diagram to calculate a statistical eye diagram. That's what I need. This is the step response that I have. Yeah, you driving with a step, and you are seeing the signal how it arrives at the transmission. And now I go to the post processing, define an eye diagram, statistical eye diagram, unit interval. Yeah, that's difficult. Let's go for 5 nanosecond. I select the step response from the task that I have defined. So differential transmission will be the eye diagram for the differential mode. And now it's calculating this in the background. It's using the step response and calculating the statistical eye diagram. Not calculating yet, I have to update it. It was just a definition. Takes a second. Here we go. Here's my eye diagram. Okay, that's how it's looking. You see this overshoot that we have seen before. They are, of course, clearly visible in here. So basically up to here, we did an analysis of this differential trace pair, which is of course not well designed. It was just quickly drawn by myself. Took about 30 minutes to get to here. And now I would like to add some stitching vias. That's what I would like to do. And the nice thing is we have such a management of simulation projects. So everything I have defined up to now, I would like to reuse. And I don't want to save it as a different project. And what I can do, I can generate a so-called simulation project. So I go here and I say I want to have a simulation project, all blocks as 3D model. Basically, it's generating a copy of everything that I had. It's linking it to the master geometry, but it allows me to modify the master geometry without, it allows me basically in the simulation project to do modification to the geometry without interfering with the existing geometry. So that's, I'll show you how it works. So I just call it stitch, that's it. It should be a high frequency using the frequency domain solvers, exactly what we did. And now it's generating such a simulation project for you. Says creating simulation project, and it will appear here as a task in the tree. You will see it will get a different icon. It's opening already here. It's called Stitch. So this project is now completely linked to the master project, to the differential pair. But it allows me to continue working on it. And the nice thing is it copies everything. It didn't just copy the geometry, it copies all the settings, it copies even the schematics that I have defined. So let's go here and now add the stitching vias, right? So take this one, transform it, copy it. And now what's the distance we would like to have? Let's give 0.6. That's it. Take this via 0.6, copy it. Okay. And now I don't add anti-vias. So of course, if I hide all dielectrics from here, you see they are stitching here. It's ugly, but it's demonstrating what we want to do. And that's it. I just added the two switching vias and I can start the solver right away. I didn't need to do any further changes. This is a beautiful way how to, let's say, include variations of your model, include variations of your geometry, all packed into the same model. And also comparing these results between the one with the via and with the stitching via and without the stitching via, it can be now done very nicely. We just need to wait till the solver finishes for the second model. So there's now the second model including the stitching vias. In port modes doesn't change that much. We should not expect that there is any change. We just change the geometry down here. Let it run the mesh adaptation. It takes just a few, less than a minute probably. It's already at the pass 2. And then we will see. I mean, first of all, we'll change. Honestly, I mean, I tried this a little bit before. We won't get our eye better with the setup just by adding these two stitching vias, which have been randomly placed to the left to the right. In a real setup, you would make a much more throughout analysis. But what we will see is, of course, that by adding the stitching vias, the propagation of the common mode changes completely, obviously, because now the layers are connected to each other. So a common mode can propagate also at low frequencies, like we see this before. So I go to the S parameters, which are still in the calculation, but you can clearly see, you see now, if we go back to the model without the stitching vias and looked at the S parameters, we don't even need to read the values here. You can see this was the differential mode transmission and this was the common mode transmission, which didn't happen at low frequencies. Well, now if we go to the stitched model, you can see both two curves going up here. So differential and common mode transmission, which is now happening due to me adding the stitching vias. You might ask yourself, why is the guy in SI talking so much about common mode? My background is, of course, in EMC, and in EMC everybody talks about common mode, so I cannot get rid of my background down here and choose the common mode to demonstrate these differences with the stitching vias. Okay, maybe for signal integrity engineers, they won't look at this, but clearly, if you would route your signal now away from the board over our cable, you should keep a very good eye on the common mode. So that's finished now. We have the S parameters, and we'll go back to the circuit. And now this is the circuit for the project Stitch, right? So this is the circuit. There are no results yet. So this is now the same circuit I have defined for the master project. It's the same circuit now, which is connected to the model with the stitching wires. And I just hit the update. All the task, everything is already defined there. It's done using EDM. So let me abort this one more time and set this one to EDM. If you have the EDM tool, I recommend to use it. You see the message is now different. We are using EDM for vector fitting. It's calculating the circuit. We can see, so the first one was this PRBS sequence. Like I said, our signal, differential signal, didn't get that much better. The I is probably also very similar. We can just let it finish and we can nicely compare. So I go to the statistical I for the stitched one and I go for the statistical I of the unstitched, and you can just click here. You see, I mean, there was, with the unstitched, there was a slightly higher overshoot, but overall you still see this overshoot. It's a little bit higher for the unstitched case. But what we might, for example, now take a look at is comparing the common modes. So in the step response, let's go to this PRBS signal. So I take the PRBS signal of the differential pair without the switching, and I say the common mode transmitted. You can drag and drop into those results. And the good thing is, because the stitching model is a part of the main model, I can easily go here, go to schematic. I can access the results from the stitched. Go to tasks, tran 1, TD voltages, common mode transmission, paste it here. And you can see the difference in the differential to common mode conversion. By adding the stitching vias, it actually got better, because the common mode is terminated at the two ends now and can propagate through the structure, while without the stitching mode this was not possible. So very nice thing, and very easy to use. So you see, it took me now 36 minutes to demonstrate it, and actually brings me to an end here. I hope you have enjoyed this quick tutorial. Was packed with a lot of keyboard shortcuts and everything. Maybe you need to watch it a little bit shorter, with a little bit slower than I was speaking to, but I'm planning to do more of this kind of tutorials for the future, and therefore you should not forget to hit the like button and subscribe to my channel. And that's it. Have a good time. Thank you. Bye bye.